Thank you. And so today, really what we're going to be talking about is intrusive magnetism on the moon. And it's a bit late in the day, so before we jump into magnetism that we can't see, I thought we'd start off with volcanism that we can see to motivate the question a little bit. So here we have the moon, and shown in lilac here are the mare of the moon, and shown in lime green are cryptomare. And what we see is that the mare seem to be distributed primarily on the near side of the moon. They're extensive, they're largely filling the basins. And this is a pretty large surface of the moon that is covered. In fact, if you look at the surface area coverage, the mare cover about 17% of the surface area of the moon. If you include cryptomare, which were mare that were emplaced at the surface initially but have been subsequently covered by basin ejecta deposits, that moves up 2%. So now you're looking at 19% of the surface of the moon is covered with basalt. However, this represents only a small fraction of the melt that was produced during the thermal history of the moon. In fact, if you do a thermal model for the evolution of the moon, you find that the volume of mare on the surface represents only about 1/10 of the magma that was produced during the history of the moon. So the question is, where is the rest of this magma? And the answer, as Jim hinted at, is that it's riddled through the crust in these intrusive magmatic deposits. And so the question that's really motivated my research for the past several years is, how can we find this intrusive magmatic component, and what can we do with it, and what will it tell us about the history of volcanism on the moon? So yes, we're looking for evidence of this intrusive magmatism on the moon. And to do this, we use something called floor fracture craters. They're a class of lunar craters. There are about 170 of them. They have a large diameter range from 13 all the way up to 208 kilometers, so a very large range of sizes are affected by this process. And there are 8 morphologic subclasses that define these craters. Shown here on the right, we have the crater Humboldt, which is a very classic floor fracture crater. You can see the fractures on the floor for which these craters were named. This crater also has large deposits of mare material on the edges of the crater. This is the distribution of floor fracture craters across the moon, and you can see it actually mirrors quite closely the boundaries of the mare deposits on the moon, and this hints at their formation process. So they're primarily clustered around the edges of the basins, a lot in South Pole Aitken Basin, and not really many out in the lunar highlands. And once again, as Jim hinted at, this is really a function of the crustal thickness during the time of emplacement, and that if you have very thick crust, you're not going to get dikes close enough to the surface to stall and see these intrusions. So here's some of the most interesting features that we'll be looking at in this talk, and these are actually the surface volcanic morphologies that are observed in floor fracture craters. So shown here on the far left, we have a vent. This one is actually from Schrödinger Basin. It's a beautiful vent located along a fracture. We also have dark halo deposits, which is what Erica was talking about in the previous talk, and these are pyroclastic eruptions surrounding vents located along fractures and observed primarily in floor fracture craters. So we're starting to see this evidence for volcanic activity within these craters. And then finally here we have crater Humboldt on the far right again, with these patches of mare material along the edges of the crater wall that actually seem to superpose certain fractures, indicating that something is happening at depth, which is then manifesting on the surface of the crater. If we want to look at this in a schematic formation process, what we have is a dike which propagates from depth. It then stalls in the shallow subsurface beneath the crater. It then, after stalling, it propagates laterally to form a sill, and this sill will extend to the edges of the crater floor before pinching off. And the sill then evolves into one of 2 end member morphologies. You either have a more classic laccolith type morphology or a tabular sill morphology. And these morphologies we've observed in the actual Lola topography, and you can see very beautifully at upward domed crater floors and then very, very flat crater floors. These morphologies have also been confirmed via theoretical modeling of deformation of elastic sheets. So we're pretty sure that this is actually what the intrusions look like beneath the crater floor. And the reason as to why there are 2 different morphologies, it's actually a relationship of the scale length of the intrusion itself. And that if you trap an intrusion beneath a small crater floor, it's going to wind up with a more domed shape. And as you extend the edges of the crater floor, you widen that diameter. The sill is going to continue to extend to fill that, and you'll end up with something that looks more tabular in relief. So the question is, okay, we've got a lot of these craters, 170 of them across the lunar surface. what volume of magma does that actually represent? If we're once again on this trail of intrusive magmatism on the moon, how much magma are we looking at from this shallowest contribution of the dikes? Well, we can use the floor morphology, which we get from Lola topography, to analyze how thick this intrusion might be. So from the work of Pike, you can calculate the theoretical depth of a crater floor for a given diameter, and then you can use the Lola topography to look at what the crater floor depth actually is, and from that you can approximate the intrusion thickness. The intrusion shape, whether it's a dome shape or a cylindrical shape, can also be inferred from the topography, and from this you can calculate a theoretical volume for an intrusion beneath each crater. And when you do that for all of the floor fracture craters on the moon, you get an estimated volume of 3 times 10 to the 6 kilometer cubed, which is nice, but to put it in actual perspective, what we're looking at is 30% of the Mare volume, which is a lot of magma. That's a lot of magma in this shallow subsurface in these craters. And so the question that comes up is, 1, how did this magma evolve once it was in place there? And 2, can we actually see it? Can we use some of our new assets and some of our new data to find more evidence of these intrusions? And for that, we turn to the GRAIL mission and to look at the gravity data to see if we can find evidence for these intrusions. For that, we're going to use Bouguer gravity data. And here we have on the left vision of the moon in Bouguer gravity space, so you can see the variations in mass within the crust. And the real heart of this analysis and why we're going to use it to look for floor fracture craters is the very simple fact that Mare basalts are denser than the lunar crust, which means that in Bouguer gravity space, they should light up as a positive anomaly. And it should be readily visible and identifiable for us. So that's why I said we would predict the intrusions to have a distinct positive anomaly. What we have here is a model of a synthetic Bouguer gravity anomaly for the crater Humboldt. This is modeling work done by Thuray et al. And so you have a crater here, and exactly like we would predict, you see this broad positive anomaly. This is about 40 milligauss in magnitude and extends almost the entirety of the crater floor, and this is for a sill-like intrusion. It's beautiful. You have the crater over here. And the question is, well, what do you actually see when you look at the gravity that we get from GRAIL? And the answer is significantly more complicated than we had initially anticipated. So what we have here is on the left, a Bouguer gravity band-filtered Bouguer anomaly for Humboldt crater. This is orders 100 to 600. And we filter it in this way to remove contributions from deep in the mantle. So Humboldt is a very large crater, and during the formation process, there actually would have been significant mantle uplift, which contributes a positive anomaly to the crater. So we filter that out by looking at these higher order contributions. And you can see there's an extremely heterogeneous signal in the crater. There's an extremely heterogeneous signal in the crust. But just looking at the interior of Humboldt itself, we can see these 2 lobes of higher positive Bouguer anomaly. They're about 20 milligauss in magnitude, but they're not continuous over the entirety of the crater floor. They do, however, seem to be spatially correlated with these 2 Mare patches that we can see on the floor of the crater Humboldt. And if you extend this analysis to all of the large floor fractured craters on the moon, say those of diameter 100 kilometers or greater, they all show this same general association. There's an extremely heterogeneous signal, but there is a spatial correlation of large positive anomalies on the crater floor with the surface volcanic features. And so this got us thinking, what could possibly be causing these variations in density in the intrusion? Is it the intrusion actually doesn't extend through the entirety of the crater floor, perhaps? Well, the topography data show that that's not likely. They show that the crater floors are flat and that intrusion likely extends over the entirety of it. So we're looking now for a process that will affect the crater density, or the density of the intrusion, without greatly affecting the morphology of the intrusion. And for this, we come to an incredibly natural magmatic process, which is actually incredibly happy for us, and that's the normal evolution of a magmatic body beneath the crater floor. Here on the upper left, we have a schematic of the processes which will take place during the thermal evolution of an intrusion. You have crystal settling, solidification, possible volcanic eruptions, and most critically for what we're going to look at here, you have a buildup of volatiles. There are a couple sources of volatiles which are active here. The largest contribution is carbon monoxide. And this is carbon monoxide, which is produced via smelting reactions in the magma between carbon graphite and metal oxides in lava, and produces a large component of carbon monoxide, which can be used to drive eruptions. And this has been known for a while, but really what hasn't been looked at as much is how this affects the density of the intrusion. And the initial modeling that we had showed and what we had done our predictions on was based on degassed lunar basalt density, which you can approximate as, say, 3,000 kilogram per meter cubed. But if you start to add in foam, if you start to add in these volatiles which have built up, you begin to drastically affect the density of your intrusion. So that's what we've shown here in the plot down at the bottom. On the x-axis, we have volume percent of foam. On the y-axis, we have intrusion density. I've plotted the average lunar crustal density for reference. And for a variety of for critical gas volume fractions, as you begin to add the foam, you begin to drastically decrease the density of the intrusion. In fact, here for, say, 25% foam, you're actually well below the density of the lunar crust, and you'd be producing a negative anomaly for these regions. So the question is, well, how does this then relate back to the craters that we've been looking at? So we'll return to Humboldt, and looking again at these spatial relationships, what we have here in the surface volcanic morphologies are evidence of degassing in the regions beneath these features. So in order to extrude the mare up onto the surface, you would have had to degas that region of the intrusion and extrude the mare up. So you would predict to have a denser intrusion, a degassed basalt beneath it. However, the regions where you don't have evidence of surface volcanic morphologies, there's no evidence for degassing of that intrusion. And you might predict you still have a foam component there, and thus a less dense intrusion. And that would manifest itself in the Bouguer anomaly, where you have a less positive Bouguer anomaly, or even perhaps a neutral Bouguer anomaly around 0 milligauss, which is indeed what we observe here in Humboldt. And again, this conclusion extends to the other floor fracture craters that we've looked at, where you have degassed basalt correlating with the volcanic features and the Bouguer anomaly, and then regions which have not degassed have a much lower Bouguer anomaly, indicative of this retained foam component. So to reiterate here in the conclusions is that variations in foam gas density and foam volume will have a significant effect on the overall intrusion density. The process, as outlined, explains the observation that there is a correlation between higher Bouguer anomalies in crater floors with the surface volcanic morphologies, and the inverse correlation regions where you have no volcanic morphologies, you have a much lower Bouguer anomaly. I'd also like to point out, note down here is that this project actually really shows the beautiful confluence of multiple data sets, where you have the gravity data set influencing our knowledge of the volcanic processes and the observational data sets influencing our knowledge of where these bodies might actually be. So with that, I'll take questions. Thank you.
Do we have any questions?
Dan Moriarty, Brown University. So I guess my question is, how deep are these intrusive layers buried? And might they be exposed by subsequent cratering? We could kind of test these hypotheses.
Yeah, it's a really good question. So if you do flexural modeling for the deformation of the floors, you can estimate that they lie about 3 to 4 kilometers, so in that range, a couple of kilometers beneath the crater floor, which means that if you have a superposed crater on the floor of one of these floor fracture craters, and it's, say, above 10 kilometers or so in diameter, you actually stand a good chance of starting to excavate some of this mafic material. And I've done a cursory look at this, and there are actually several candidate craters where you might have excavated some of this mafic material. So that definitely be something interesting to look at to confirm this hypothesis. And it is also part of my thesis. So stay tuned for next year's Exploration Science Forum.
Any additional questions? Thank you very much. With that, we'll move on.